Welcome to the AI and GIS Frontier podcast. This is our first weekly update episode, and we have a lot to get through. Drew, what is the big picture this week?
This was arguably the most significant week for autonomous GIS since the concept first appeared in the literature. We had 3 independent GIS agent systems publish results above 85% accuracy on multi-step spatial tasks, all within the same reporting window. Google announced a major new agentic framework for Earth observation. Digital twins are going AI native, and there's a fascinating paper applying LLM as judge evaluation to drone-based powerline inspection. On top of all that, the precision agriculture space had some notable moves, and the open-source Geo AI ecosystem hit some real milestones. So let us work through all of it.
Let us start with the biggest story. Google geospatial reasoning. What did they actually announce?
Google Research published a framework called geospatial reasoning. The core idea is building agentic workflows that integrate multiple Google Foundation models with developer datasets. This is not a single model you call, it is an orchestration layer, where an AI agent can plan a sequence of geospatial analysis steps, retrieve the right data, run inference through one or more foundation models, and synthesize results. The critical detail is who the launch partners are. Airbus, Maxar, and Planet Labs are the initial testers of Google's remote sensing foundation models within this framework. Those are the 3 largest commercial satellite imagery providers on Earth. When Google gets those 3 companies to beta test an agent framework, that is not a research demo. That is infrastructure.
How does this relate to the Alpha Earth model we discussed in a previous report?
Alpha Earth Foundations, which is Google DeepMind's satellite embedding model, is one of the foundation models that plugs into this framework. But geospatial reasoning is bigger than any single model. Think of it as the operating system layer. Alpha Earth provides embeddings. Other models handle segmentation or change detection. And the agent layer decides which models to call, in what order, on what data. The shift is fundamental. We are moving from an era where a GIS analyst decides which model to run on which data, to an era where an AI agent makes those orchestration decisions. Google is not selling you a model anymore. They are selling you an agent that knows how to use models.
That connects to the other 2 agent systems that published results this week. Walk us through those.
Penn State released what they are calling GIS Copilot. It is a collaborative human-to-agent assistant, similar in concept to how GitHub Copilot works for code, but built specifically for multi-step spatial analysis. They tested it across over 100 multi-step guided spatial tasks and achieved about 86% success rate. These are not trivial tasks. We are talking about things like taking a natural language request for a watershed analysis, decomposing it into the correct geoprocessing sequence, executing each step, and validating the result. 86% on that kind of task, complexity is significant.
And Supermap shipped something too.
Supermap released Agent X Server, which includes what they call a spatial agent. The positioning is different from Penn State's research system. Supermap is a commercial GIS platform, and they are shipping the agent as a product feature. You talk to the spatial agent in natural language, and it operates GIS tools on your behalf. The framing from Supermap is that this opens GIS capability to anyone, not just trained analysts. Now combine these 2 with the Geo Agentic RAG paper from our last report, which demonstrated 85.3% pass rate and 88.3% answer correctness on geospatial task benchmarks. That is 3 completely independent systems, built by different teams using different architectures, all converging on the 85 to 86% accuracy range for autonomous spatial task completion.
Why does that convergence matter more than any single result?
Because it tells you, this is not a fluke. When one lab publishes a result, you ask whether it generalizes. When 3 unrelated teams independently hit the same capability band, the capability is real. It is like how multiple teams independently demonstrated large language model reasoning at similar levels, and within a year, it was in production everywhere. The 85% mark is also psychologically important. Below 80% autonomous GIS is a novelty. Above 85%, it becomes viable for supervised production use, where a human reviews the output, but does not have to redo the work from scratch. For a forestry company running annual harvest planning, an agent that can correctly execute 85% of the spatial analysis steps means your GIS team shifts from doing the work to validating it. That is a fundamentally different staffing model.
Mapbox also made some predictions about where all this is heading. What did they say?
Mapbox published a blog post with 4 predictions for GeoAI in 2026, and the most consequential one is about the Model Context Protocol, or MCP. They predict MCP will become the standard integration layer for connecting AI agents to live geospatial data sources. MCP is an open standard that defines how external APIs, data sources, and actions are exposed to large language models and agents. Think of it as a universal adapter. Instead of every agent framework building custom connectors to every data source, MCP provides a standardized way to say, here is my data, here are the operations you can perform on it, here is how to call them. If Mapbox is right and MCP becomes the standard, it means the GIS agent systems from Google, Penn State, and Supermap could all connect to the same data sources through a common protocol. That is interoperability at the agent level, which the GIS industry has historically struggled with at the data level.
Let us shift to digital twins. You said they are going AI native this week?
Multiple reports converged on this. RT Insights published an analysis showing digital twins are transitioning from what they call static virtual replicas to intelligent AI-driven systems. Argonne National Laboratory convened a working group on AI-enabled digital twins for U.S. cities, covering energy consumption, water management, and urban systems. And there is academic work showing the shift from a descriptive approach to a prescriptive one, meaning the twin does not just mirror the current state, it recommends actions. The key technical advance is the integration of 2 types of AI. Predictive AI identifies patterns that precede failures or performance deviations, so the twin warns you before something breaks. Generative AI creates plausible future states and alternative configurations, so planners can evaluate trade-offs before committing resources. A city planner could ask the digital twin to simulate 3 different transit routing scenarios and get AI-generated projections of ridership, cost, and coverage for each one.
And Asia Pacific is leading deployment?
According to Neuron Digital, Asia Pacific has emerged as the global leader in scaling digital twins from pilot projects to production infrastructure, driven by rapid urbanization, net zero commitments, and the need for resilient infrastructure. What is most interesting from our perspective is that digital twins were always inherently spatial. A city twin is fundamentally a geospatial system. Now that they are becoming agentic, they represent a natural deployment surface for the GIS agent frameworks we just discussed. Imagine Google's geospatial reasoning framework connected to an AI-native city digital twin through MCP. The agent orchestrates satellite-derived change detection, IoT sensor data, and simulation models in a single workflow. That is the convergence point these technologies are heading toward.
Now let us talk about something more niche but fascinating. The LLM as Judge paper for powerline segmentation. What is happening here?
There is a new paper on Ayer-Karksiev from April 8th that applies the LLM as Judge paradigm to evaluating semantic segmentation of power lines in UAV inspection imagery. To explain why this matters, let me back up. LLM as Judge is a well-established technique in natural language processing, where instead of using fixed metrics to evaluate model output, you use another large language model to judge the quality of the output. It has been very successful for evaluating things like chatbot responses and summarization quality. This paper takes that paradigm and moves it into computer vision, specifically into an operational geospatial domain. The use case is drone-based power line inspection, where you fly a UAV along transmission corridors and use semantic segmentation to identify the power lines, insulators, and potential faults in the imagery.
Why would you want an LLM to judge a segmentation model instead of standard metrics?
Because standard metrics like intersection over union tell you how well the predicted mask matches the ground truth mask, but they do not tell you whether the errors matter operationally. A segmentation model might have 92% IOU on power lines, which sounds great, but if the 8% it misses corresponds to critical junction points where faults are most likely, that model is dangerously misleading. An LLM as Judge approach can evaluate the segmentation in context. It can look at the image, look at the segmentation output, and assess whether the result is operationally useful for the inspection task. Did it capture the structurally important sections? Are the missed regions in areas that matter? That kind of contextual evaluation is what LLMs excel at.
Could this approach extend to other remote sensing applications?
Absolutely, and that is the real significance. Think about forest change detection. A standard metric tells you the model detected 90% of deforested pixels. But an LLM as Judge could evaluate whether the detections correspond to the patterns that matter for enforcement, like whether linear clearing patterns indicating illegal road building were captured, versus random noise in cloud shadows. For agricultural crop classification, an LLM judge could assess whether misclassifications are between similar crops that do not affect planning decisions or between fundamentally different land uses that do. This paper is a proof of concept, but the technique could reshape quality assurance for every remote sensing pipeline that feeds into decision-making.
Shifting to agriculture, what happened in precision ag this week?
Two significant developments. First, Syngenta renewed and expanded their partnership with Planet, the satellite imagery company. Syngenta now has access to Planet's high-resolution tasking data and PlanetScope near-daily satellite data. They are delivering this imagery to farmers globally through their CropWise digital agriculture platform, enabling remote monitoring of crop health, pest detection, and disease outbreak identification. The scale is notable. This is not a pilot program. Syngenta is one of the world's largest agricultural companies, and they are operationalizing daily satellite monitoring as a standard capability for their farmer clients.
And there was research on fusing drone and satellite data?
A paper in Frontiers in Remote Sensing reviewed the integration of UAS and satellite image data in precision agriculture. The headline numbers are compelling. UAV satellite data fusion improved crop yield prediction accuracy to an R-squared of 0.83. AI-driven disease detection achieved 81 to 95% accuracy in identifying infections 2 to 3 weeks before symptoms are visible to the human eye. By spectrally extending drone RGB data to vegetation red edge and near-infrared regions, researchers improved biomass estimation accuracy by 18% and nitrogen estimation by 31%. The practical impact is also quantified. Combining UAV and satellite data with machine learning reduced irrigation costs by 20 to 25% and decreased nitrogen fertilizer application by up to 31 kilograms per hectare without hurting yields. For forestry professionals listening, the techniques for fusing high-resolution drone data with satellite time series are directly transferable to silviculture monitoring. A lot of the vegetation index work and the multi-scale fusion approaches map cleanly onto the seedling detection and canopy recovery workflows we covered in our episode on satellite monitoring for silviculture.
Let us round out with the open-source GeoAI updates. What should people know?
3 things worth tracking. First, the GeoAI Python package, which is the open-source package from the OpenGeos project, was formally published in the Journal of Open Source Software. That is a peer-reviewed milestone. The package provides a unified framework for processing satellite imagery, aerial photographs, and vector data using deep learning models, integrating PyTorch, transformers, and specialized geospatial libraries like TorchGeo and TorchChange. Having the GIS publication matters because it gives institutional credibility for agencies and companies that need to justify adopting open-source tools.
And there is a free textbook to go with it.
Yes, the GeoAI with Python book is freely available online at book.opengeoai.org. It is a practical textbook covering GeoAI workflows for GIS professionals. For anyone who has been watching the foundation model space and wondering how to actually get started with these tools, that book is the most accessible on-ramp available right now.
You mentioned MMEarth earlier. What is that?
MMEarth, which stands for Multimodal Earth, is an academic project that created a massive open geospatial AI dataset and model. Think of it as the open-source counterpart to Google's proprietary Alpha Earth. The dataset is multimodal, meaning it includes multiple types of Earth observation data that can be used together. It has been integrated into Facebook's TorchGeo library, which is the leading open-source library for geospatial deep learning. The significance is that it gives researchers and smaller organizations access to foundation model scale training data without depending on a cloud provider. In the same way that open-weight language models democratized NLP beyond OpenAI and Google, MMEarth could democratize geospatial AI beyond the proprietary foundation models.
And the Taylor and Francis paper on open-source LLMs for GeoAI.
A paper published in the International Journal of Geographical Information Science examines how open-source large language models are shaping the future of GeoAI. The argument is that while proprietary models from Google and others get the headlines, the open-weight models are enabling a parallel track of innovation that is more accessible, more customizable, and, in many cases, more appropriate for organizations with data sovereignty concerns. If you are a government forestry agency that cannot send your data to a third-party API, an open-weight LLM running on your own infrastructure is the path forward. This paper provides the academic framework for that argument.
So to pull all of this together, what is the theme of this week?
The theme is convergence. The GIS agent capability is real. It is not one system or one paper. It is Google, Penn State, Supermap, and academic researchers all independently arriving at the same capability band. The integration layer is emerging through MCP. Digital twins are becoming the deployment surface for spatial AI agents, and the open source ecosystem is building fast enough to provide alternatives to every proprietary tool in the stack. If you are a GIS professional, the practical implication is that the ratio of your time spent on analysis versus execution is about to shift dramatically. These agent systems are not replacing spatial thinking. They are replacing spatial clicking. The analyst who understands what needs to happen still decides. The agent handles the multi-step execution.
What should people be watching for in the next 2 weeks?
3 things. First, Forest Sat 2026 is less than a month away, May 4th through 8th in Gainesville, Florida. That conference will be the most concentrated collection of AI plus forestry research this year, and expect papers that build directly on the agent and foundation model capabilities we discussed today. Second, watch for MCP server implementations in open-source GIS tools. Mapbox made the prediction, and QGIS and GRASS GIS plugin developers are likely already working on it. Third, keep an eye on the ITU GeoAI Challenge results. Teams are working with Alpha Earth and TerraMind embeddings right now, and the benchmarks they produce will tell us whether those foundation models generalize as well as their creators claim.
Great roundup. Lots to digest and track over the coming weeks. Thanks for breaking it all down, Drew.
Anytime. This is the most exciting period in geospatial AI we have seen. Every 2 weeks there is a headline that would have been a keynote talk a year ago. Staying current is a challenge, but that is why we are here.